So welcome back to all. So this is the 20th lecture of quantum mechanics series, and in this lecture I will talk about the commutating operator. I have also talked some basics about the commutating operator, and in this lecture I will talk about some special property of the commutating operator. So at first I will just give a brief introduction about what is called commutating operator. If you really want to know more details about this commutating operator, you can go back to my previous lecture where I have give a very detailed lecture about this commutating operator. So if A and B are two commutating two operators, they are two separate operators, and if A B minus B A will equal to 0, then we will say that these two operators commute with each other. So if these two operators commute with each other, then we will write a third bracket, A operator, then comma B operator, then it is closed by third bracket is equal to 0, and this operator is called commutator of A and B. If this commutator of A and B is equal to 0, then we say that A and B, these two operators will commute with each other. So there is one simple criteria for two operators to be commute with each other, and the criteria is that if these two operators A and B, if they have the same common eigenfunction, this is the kth vector n, if they have the same common eigenfunction n or psi n, then we can say that these two operators will commute with each other, or we can say that A and B will commute with each other. Okay, so this thing we will prove. So this statement we will prove that if A and B, these two operators, have the same common eigenfunction, then they will commute with each other. Now this eigenfunction, that is the kth vector n, if it is eigenfunction of both A and B, then according to the eigenvalue equation, if A operator operating on this function, as this function is an eigenfunction of this operator A, so we will get back the same function with some constant that is called eigenvalue. This constant is suppose an. Similarly, as this kth vector is also an eigenfunction of this B operator, so when the B operator will operate on this eigenfunction, we will again get back some eigenvalue into this eigenfunction. So this is basic criteria of eigenvalue equation. Now suppose we have some function. Now in my earlier lecture from the superposition principle, we have said that any function can be written as a linear combination of eigenfunction of the Hamiltonian operator. Okay, so suppose that this function f, it is any arbitrary function, this can be expressed as a linear combination of this eigenfunction, which are the eigenfunction of these two operators A and B. So we simply write this function as a linear combination according to the superposition principle. Now the commutators, like this A and B commutator, this is basically an operator, it will operate on this function. So we will see what happens when this commutator of A and B will act on this function f, which is basically a linear combination of the eigenfunctions. So if this commutator operator, the expression of this commutator operator is AB operating on the function f minus BA operating on function f. So what does it mean? It means that B operator will operate on this function first, then whatever the function it will produce on which A operator will operate, and vice versa in that case. Okay, so if we just express this function as a linear combination of this eigenfunction, we will get a summation, because we have taken this function as a sum of this linear combination. So summation n is equal to 1 to infinity, and in the bracket we will get A operator, B operator, Cn is the coefficient, into this kth vector n, which is basically an eigenfunction of both A and B. Similarly, this also occur here also, B operator, A operator operating on this kth vector n. So at first the Cn is basically some constant value, that is the coefficient value, so it will be out of this equation. So we will take out this coefficient Cn out of this equation, and we will see that this operator A operator, B operator acting on this eigenfunction n, and B operator, A operator acting on this eigenfunction n. Now at first B will act on this eigenfunction n, and after that whatever we will obtain on this A will act. Similarly this in vice versa order occur here. So you can see that first of all B operator will operating on n, and according to this eigenvalue equation you will obtain Bn into the kth vector n, and again the A operator will act on this kth vector n, and you will obtain An into the kth vector n. Okay, so if we simplify this equation we will obtain Cn An Bn minus Cn An Bn, and there is a common function, that is the eigenfunction of the operator A and B. So you can do this mathematics into your own in your home. So if you do it in your own, you can easily understood how you will came up from there this to this. Okay, this is very simple thing. So you can see that these two are same value, so these two will cancel out with each other. So we will get that the commutator of A and B when operate on this function f, we will obtain 0. So this is basically true for all value of n. So we can say that A and B will commute with each other. So we can see that from the beginning where we have told that these two operator A and B, they are having common eigenfunction n, and if this criteria is satisfied, then A and B operator will commute with each other, so that the commutator of A and B will be equal to 0. So this is the statement that if two operator commute, we can say that if two operator will commute, then they have a common eigenfunction. So this is one statement, and we can actually make this statement vice versa. So if two operator have same common eigenfunction, then they will commute with each other. So these two statements are actually vice versa statement. So the first statement is that if two operator commute with each other, they must have some common eigenfunction, and if the two operator has common eigenfunction, then they will commute with each other. Now coming back to our older lecture, where we have proved that there are two operators, that is momentum operator and position operator, and the commutator of momentum and position, these two will not commute with each other. So that's why this commutator is not equal to 0, that we have seen in my older lecture. If you go back to that older lecture, you will see that according to the Heisenberg's uncertainty, that as this the momentum and position do not commute with each other, we cannot determine the exact position and exact momentum of a substance simultaneously. This is basically nothing but a Heisenberg's uncertainty principle. So they will not commute with each other. So what does this mean? That these two operators not commute with each other. This means that if these two operators not commute with each other, then they do not have the common eigenfunction. They have different eigenfunction. Okay, as we have says that if two operators will commute with each other, they should have some common eigenfunction, but this criteria is not satisfied here. These two operators is not commute with each other, so they have different eigenfunctions. So that is why we cannot measure them exactly. So we cannot measure the momentum and position of a particle simultaneously. So they because they have different eigenfunction. So that is nothing but the Heisenberg's uncertainty principle. So up to this, if you have any doubt regarding this lecture, you can ask me through the comment section, and in my next slide I will talk about the time dependent wave function. Thank you for watching this video.